is it forms dimers. And that means that you pair up one out of those, two of those bonds associated with each atom. You're still now left with a, although I haven't drawn it here, still left with a dangling bond here and a dangling bond here. But you can see that what you form are rows of atoms. And that's your basic repeating unit, which we call the unit cell. Now, for reasons I'll not go into for the experts amongst you, what we have then is we have a coupling of an electronic and geometric distortion, which is usually called a Yam-Teller distortion, whereby the system, or this unit, this dimer unit, deforms so that one atom moves towards the surface and one atom moves away. And now nature has given us an atomic switch. So we've got this type of unit, and you can see that what they do, as sketched here, is that they buckle back and forth. And the reason they do that is that they all buckled in the same direction. It places quite a lot of strain in the next layer down. So to relieve that strain, you get this alternate buckling of the dimers. Reasonably clear? Okay. And they can buckle in phase. The rows can buckle in phase like here, or they can buckle out of phase. And we'll see examples of both in a second. So as well as having, I want to make this point as well, this idea that the distortion is not just a structural distortion. When it buckles, what happens here is you end up with a low density of states. Your second year, so you haven't done solid states, so I'm talking to the undergraduate. So you end up with a low charge density or low electron density on this atom and a high electron density in this atom. When it goes that way, then this becomes the high electron density, this becomes the low electron density. So as well as having this mechanical switch, you also have an electronic switch. But you can go further, because one of the interesting spins that was placed on this quite some time ago, before the experiments were actually feasible, was that when you look at this, then you can label each one of these with what's called a mechanical spin. Just as in magnetism, you have an interaction between the spins of the electron, and there's something called the Ising, more correctly the Ising model, for modeling magnetic systems, where you basically have spins on a lattice and you control the interactions of those spins. Many people have looked at this as a mechanical analog of the Ising model, where the configuration of the dimer represents a spin. So you have something that looks like that. And the question then is the system frustrated? Can you flip one of these individual spins, or does the interactions between the spins, between the dimers, preclude that? Indeed, and this was a very interesting idea, and this was actually, along with the sort of Drexler, the more grandiose Drexler stuff, this was something that really drove us to explore this in detail. There would be suggestions as far along ago as 1996, which weren't pursued up until a couple of years ago, that you could actually do dimer logic, that if these dimers can communicate with each other, then you can set the system up, flip one dimer, and you get a cascade or a domino effect, which gives you an output somewhere else, and you could do dimer logic. Now, before we all get too excited, well, let me explain, and then I'll explain why we shouldn't get too excited about that. So the idea here is, you bring your tip in, that's a 1, this is sort of more from a storage capacity, and you flip it and you get a 0. But you can also think of using these, setting up predefined arrangements of dimers in different states, and then flipping the 1 on the end here and having the output up here, for example. So you get them to communicate. Now, so ultimately, could we have an atomic version of Charles Babbage's difference engine? Could we do mechanical computing, but all the way down at the atomic level? Operating 5 degrees above absolute 0, in ultra-high vacuum at a pressure comparable to that you get on the moon, and at sub-Hertz bandwidths, because it takes us about 20 minutes to take a scan. So, you know, this is not going to be a viable technology. But believe it or not, there are reasons we do research other than to develop applications. Right. So, well, let's leave the phasons thing aside. That's a bit of a side issue, which I might come back to. But what we have, here's finally we've got, oh, well, that one's gone. Finally, we've got onto the experimental results. Here's an image, and this edge here is a step edge. One of the most common defects when you look at a surface in a scanning probe microscope is that you see steps. The surface is never perfectly atomically flat. And so you can see the dimer rose running here, and just due to the crystallography, the direction of the dimer rose flips on this side. And you can see the buckling. This is actually at 77K, and what's interesting is because the barrier, the energy barrier between that state and that state is quite low, it's of the order of 100 milli-electron volts, it means that once you get up to, well, 60, 70K, they start to flip back and forth, which is one of the reasons, well, which is the key reason we go to 5K, because we don't want that happening while we're trying to manipulate things. And so you can see here it's very well defined, but in other regions it's very fuzzy here, and it looks like you don't have any of the zigzag buckling, and in fact it's because the dimers are moving back and forth at a rate much faster than they can scan, which really starts to speed up once you get to about 200K. Okay, so this has been looked at in depth, and you can see the noise. Well, the contrast isn't great, but I hope you can see the noise. You can see it's pinned here, but then in other areas, particularly up here and over here, you can see that there's noise just flickering going on, which is why we go to 5K. So I don't know how many people in the audience, in terms of postgrads and members of staff, do scanning probe microscopy. 2, 3, 4. Okay. So those who've done scanning probe microscopy may well have done STM. You look at that image and go, that's an awful image. And yes, it is indeed. But what's quite interesting is that a tip that gives you very good scanning tunneling microscope images may not give you good atomic force microscopy images, and vice versa. The great thing about this system with the tuning fork is that because it's a metal tip, and we've got a connection to that to measure current flow, you can do both scanning tunneling microscopy and atomic force microscopy, with some provisos which I'll not bore you with. So we first of all prepare a tip, make sure we get atomic resolution, and then we switch to AFM feedback, which is where we have here. And now we're in atomic force mode. This is telling us the value of the frequency shift we're setting. So the difference in the frequency out here as compared to here. So the larger more negative you make this value, the more attractive the interaction between the tip and the sample is becoming, and the stronger the interactions will become. So you can see already that as we scan, we're getting a large interaction with the surface, and these dimers are flipping back and forth. Which is all well and good, but not particularly controllable, but give us hope that the experiment is actually doable. So the experiment we want to do, finally, is this. We have our zigzag dimers, we bring a tip in at this point, and then the question is, if we flip that, we bring the tip in, cause a strong interaction, and bring the tip back out again, do we get something like that, which we call 3 in a row for obvious reasons? Or, and perhaps more interestingly, do we get longer range correlations? Do we see correlations like that? Or do we see things happening like that? Or do we see even something which is longer range than that? So, finally, this is the key experiment. So this is, you can see this zigzag buckling of the dimers. So here's our up atom, here's our down atom. When I say up atom, I mean this one, obviously, compared to that one. And you can't see the down atoms because we haven't brought the tip in close enough deliberately, and also the resolution on this image is quite poor, and that's deliberate because we want to keep the tip well away from the surface. So what we do is we select a down atom, which we can't see, but we know from symmetry it has to be there. We bring our tip in, and let me just go back up again, and you can see what happens. This one flips, but also the one beside it also flips, and that happens every time. We can then restore it. We can take this structure and we can return it back to its native state. It turns out that there's actually less force required, which I'll explain in a second, or show in a second, to go backwards than there is to go forwards. For the nanotechnologists amongst you, I just want to highlight this, not because I want to flag up Nottingham's publications, or at least not only because I want to flag up Nottingham's publications, but this is a very important journal. The Bioscience Journal of Nanotechnology is entirely open access. You don't have to pay as an author, you can submit your articles to it, there's no fee, and it's got an extremely good editorial board. There are lots of, notwithstanding our work, but there are lots of good papers published in there. So I just recommend those of you who are in nanotechnology to think strongly about contributing to this journal. It's, I think it's a model of how open access should proceed. Unfortunately, it's not the easiest of business models to implement, but you know, we're publicly funded and therefore our work should be going into the public domain. So, images are fine, but of course we want to get a bit more quantitative analysis here. And because the way we do this experiment, we do it via spectroscopy. So we oscillate our tip up here, we measure the frequency shift, and then we bring it in and we measure the change in frequency shift as we bring the tip in closer and closer to the surface. And so the flips you saw on the previous slide, this is exactly the way we do it. So the open circles of this approach, you reach a threshold point where bang, the atom jumps towards the tip, you see a sharp change in the resonant frequency, a sharp discontinuity, and then when you come out, again, you see it comes along a different trajectory, which is clear because the atom's now in a different position. And what you end up with is what's termed a hysteresis loop. You're coming out a different trajectory than the one you did. Interestingly, you go the opposite direction, you see a smaller shift, and you see a smaller force required to restore this structure. Though it very much depends on the potential energy landscape, it very much depends on the environment of those atoms. One thing we wasted a huge amount of time over, and it was one of those moments when you realise after 3 months, why are we doing this? This is just stupid. We wanted to see whether we could get access to dissipation and dynamics here. Because I mentioned that we measure the resonant frequency of the tuning fork, but I also mentioned that we keep the amplitude constant. Because we keep the amplitude, well, the way we keep the amplitude constant is we pump energy into the system. So we know how much energy it takes to keep the amplitude constant. Therefore, we know in principle what the dissipation is. And we were very keen to try and link that dissipation, and many in the past have been very keen to link that dissipation to processes happening on the surface, perhaps phonons, coupling to phonons, electron-phonon interactions, etc., etc., etc. And we spent a lot of time working on that, and it was completely and utterly irreproducible. Sometimes we do the experiment, we see no dissipation within our noise. Other times we see whopping amounts of dissipation. This is electron volts per cycle. Typical silicon bonds are of the order of 1.6 to 1.7 eV. We're seeing all the way up to a few electron volts of energy. And turns out that what's important here is not what's going on at the surface, it's what's going on at the tip. That atom at the surface flips on one cycle. Notice that this is dissipation per cycle. The tip is oscillating back and forth 25,000 times roughly a second. That flip event happens on one cycle. We are not sensitive to that flip event. You work it out, it's below a noise level. What we are sensitive to is how the tip atoms are changing on each cycle. And that's why in some cases we see no dissipation, because the flip event is below a noise level, and in other cases we see a whopping amount of dissipation. It's entirely dependent on the tip. Yeah, we started at half 2, didn't we? Only another 2 hours left. So the great thing as well is because you're measuring that frequency shift as a function of tip sample separation, and because that frequency shift depends on the force, in a fairly non-linear and quite tricky method, it was really only 2004 when people worked out how to extract for any arbitrary oscillation amplitude the relationship between the force and the frequency shift. I'm not going to go into that, I promise. But what you can do is you convert your frequency shift versus tip sample separation into either a force versus sample separation, or just as easily potential versus tip sample separation, which we call traditionally Z. So you can measure the force of a single bond. Now, this was back a little over a decade ago, was the first time this was done for a different type of silicon surface. This is a silicon 111 surface, so if you imagine taking that cube, that basic repeating unit cell, and cutting through that diagonally, the plane that you expose then will be a 111 plane, and because it's a different symmetry, you get a completely different arrangement of atoms. And so we can extract, this is our data, these are in good agreement with what's gone before. Had never been done for the silicon 100 surface. If anybody is thinking about getting into Q plus measurements, because we got into it relatively, non-contact AFM using a Q plus sensor, because we got into it relatively recently, we were somewhat surprised at the level of rigour, or in some cases the lack of rigour, with regard to experimental uncertainties. There are a large number of uncertainties there. So in principle, you can measure forces down to piconewton levels. In practice, in many cases, it's very difficult to quote to that level, but I'll not bore you with that. So we use a number of different strategies to measure the force. In particular, we spend a lot of our time running large simulations, density functional theory simulations, to really look at the dynamics of the bond formation and to look at the type of potential energy surface we have and the magnitude of the chemical bonds that we form at this surface. And as you might expect, we get, this is a very busy slide, I really don't want you to take it all in, but we get very good agreement with the theoretical calculations if we choose the right tips. And in principle, we don't know what our tip, not in principle, in practice, we do not know what our tip state is. So it's a question of trying to come up with the most plausible types of tip, and we have hints in terms of what the dissipation is doing and how the tip overall behaves, what that structure might be. But we are basically trying to use the calculations to extract some information about the tip. That's not ideal. It's important to have a loop between feedback, between theory and experiment. But what you don't want to do is to try and force your experimental data to match a particular theoretical result. So, I'll tell you in a second some different strategies we have to analyse the tip. We put that all together and you can do neat things like this, where the idea here is to recover that type of zigzag symmetry. There were two defects in this, which I'll play again from the start in a second. This is speeded up quite dramatically. This was 10 hours of a postdoc's time. Manipulate, scan, manipulate, scan, manipulate, scan. Because we're working in ultra-high vacuum and because the Q in this case was something like 30,000, it takes a long, it's a very high quality factor, so it takes a long time to do this scan, even though it is frequency modulation. Right. The trouble with tips. Oh, scanning probe microscope is guilty secrets. So this is a silicon 100 surface. It's the same surface, and in many cases it's exactly the same sensor, and it's just different regions of exactly the same sample. And what you can see is that, well, in many cases you sort of get the structure you'd expect in terms of the zigzag buckling. It's this dimerized structure I mentioned before. Then in other cases, you get these things which are absolutely bizarre. So these half-crescent shapes, so these crescent shapes with sort of smarties, or down here we've got pear drops, the things which look like sort of lines here. You've also got things which look like rectangles. And it's telling you a great deal about what's happening, what's going on at the tip. But you try to publish this, and what you get back is, well, actually the tip effect's just a nuisance. You know, everybody knows that what you do is you keep doing your experiment until you get the same images as everybody else gets in the literature, and then you publish those. Very dangerous way to do science, because there are countless artifacts which have been interpreted in terms of true surface structures. Not that I'm bitter or anything. But it is frustrating, and John Pethica, who is now in the National Physical Lab, was in fact Billy and Rohrer, who invented the AFM, attribute the origin of the idea of the end of the concept of the AFM to John Pethica, who said, well, actually, when they first developed the STM, well, when you've got a tip this close to a surface, you've got to have forces there. And it was that insight which led to the development of the AFM. John says, back at a conference a few years ago, made exactly the same point, is that scanning probe microscopists have hundreds and hundreds of images on their hard disks or in the drawers of the filing cabinets which they don't understand. And we need to find ways of understanding those, because we're throwing away a lot of important data. And it doesn't just depend on the topography that we measure, it depends on the effects, the currents that we measure, the effects of dissipation we measure. As you might expect, some tips give us a whopping amount of dissipation because the atoms are moving around a lot, others give us very little dissipation. And while you're scanning, here's the stuff that we don't publish. Here's a typical event where you're not getting atomic resolution, you're seeing the defects, but you're not getting atomic resolution, and bang, you get a spontaneous change. We sometimes apply voltage pulses, and that's what's going on here to the tip to get it to change and you can see you get a wide range of different images. Q plus is even more extreme. It goes from nothing at all to very good resolution to back out. You know, it's a beautiful technique and it's a fun technique when it works. When it doesn't work, it's the most frustrating thing on earth. So, how do we characterize the tip? I'll tell you quickly about in the last 5 minutes or so about two methods. One of which, as I mentioned right at the start, is we exploit the surface. We use bonds, orbitals at the surface, which have a narrower spatial extent than the orbitals at the tip. So the surface atom's orbit is sharper than that of the tip. And this was, I have to point out, this was Franz Giesecke who developed this Q plus technique. Back in 2000, he pointed out that this would be possible. To a great deal of skepticism, many people thought that the features he was seeing, and it led to a comment in the following issue of Science, that there were feedback artifacts. They're not feedback artifacts, and I'll give you, well, what I call incontrovertible evidence that what he suggested was possible is indeed possible. So C60, Buckminster fullerene, many of you familiar with it. Okay, 60 carbon atoms, it's in the shape of a football. Basically, if you took a football and shrank it down by 10 orders of magnitude, putting an atom in each vertex, that you get C60. Nice line molecule, we like it because it's readily identifiable and easy to manipulate. So you can, here's before, you take molecule here, and there's a defect here just for registration. You pick up that molecule. I'm not going into the ways we can pick up that molecule, but it's relatively straightforward. And what you see is that the atoms no longer look nice and round and circular. They've got this sort of double-lobed structure. And that's because what's happening now is that the radius of curvature of the tip is larger than the radius of curvature of the orbitals of the surface, so you're imaging the tip. And that's very useful because we can now then take our C60 molecule and with our theory chums in Nottingham, explore what we'd expect if the molecule were pointing with a double bond down towards the surface. We've got something which is double-lobed like that. Or a single bond down, or importantly, of course, for C60 you have hexagonal and pentagonal faces, and five-fold symmetry is not that prevalent amongst molecules in nature. So to give strong evidence that you've actually picked this molecule up on the tip and it's not some other weird tip, you really need to look for pentagons. And now the first hints of pentagons are here. I wouldn't bet the farm on this, but you can start to see a little bit more sort of circular symmetry with the node in the middle. But the problem with, the thing with STM is that it's giving you images which are due to the electron orbitals, and those electron orbitals can be relatively delocalized, so you can't get the resolution you want sometimes. However, if you move to non-contact AFM or dynamic force microscopy, what you then find is that the contrast is due to the formation of a chemical bond between an atom at the surface and an atom at the tip. And what you can say, I hope here, is that you can see 5 atoms, 1, 2, 3, 4, 5, and they're repeated because each atom at the surface is imaging that structure in the end of the tip. There are lots of neat things about this in terms of the contrast between the two halves of the unit cell, etc. But we can change, albeit in a sort of trial and error way at the moment, we can change the orientation. And that's important because with fullerenes you get a difference between the bonds in the reactivity of the bonds. You can do different chemistry with different orientations. And what you can also, let me just skip through all of this, given that time is pushing through. What you can also do, of course, is that if you've got a molecule on the tip, you can go and find another molecule on the surface. And I don't know how many of you have done this type. Have you seen Leonard-Jones potential, Morse potential, anything like that in terms of atomic basic? No? Okay. The later undergraduates and the postgraduates will have seen that. What you do, believe you me, you'll see Leonard-Jones and Morse potentials and that type of, those type of potentials which are used to model the interactions between atoms and molecules. And so this is our experimental data. You can see what's called the Girofalco potential, which is the theoretical potential for two C60 molecules. And there are, particularly around the minimum here, which is what we're most interested in, you can see there's damn good agreement. There's no fitting here. There's basically, we've just taken the theoretical curve and overlaid it on the experimental data. There's no fitting at all. Some discrepancies here, some discrepancies there, which if you want to ask me any questions later on, I can cover. And finally, one final show of hands. Are many of you familiar with PhDcomics.com? Ah, that's good. That's good. Go and have a look, not in work time, do it at home on your own time, otherwise you'll spend an awful lot of time reading these. But anyway, here's the professor, and this is the way it usually works in terms of research. I don't get it. There are machines that can do this 10 times faster now. Why don't we just buy a new one? So we just do cost-benefit analysis. Oh, when I say cost-benefit, they don't usually mean okay. So what you generally do is you fling lots and lots of students at the problem. Physicists are bad enough for that. The worst are the organic chemists. They throw huge teams of students at the problem. And sometimes you need to sort of stand back and think, okay, well, I'm getting results this way, but is there a better way of doing it? And what we've been working on, and I haven't got time to take you through all the details, we've been working with colleagues in computer science on using genetic algorithm approaches, a range of different approaches, to basically have a fully automated system. So what we've done here, this isn't on a vacuum system, this is on a standard entry-level system that works in air. We take our sample, it's actually graphite, and we peel off the top layer to clean it, or to cleave it, put it under the microscope, cut our tip, put that in the microscope in the STM, move the tip towards the surface, just coarsely, and then walk off. And the system tunes itself. So it's a pretty poor tip to start off with, doesn't work. It's applying pulses, it's doing other things like touching the tip off the sample, things like that. You can see this is the computer telling us what's going on. We've recently translated this to vacuum, and the reason I'm very excited about this is that I was on one system in our lab, one ultra-high vacuum system, while this software was working on another system, and it beat me a number of times in terms of getting the tip state sorted out. And so it gets to this point, tells us it's got an atomic resolution. That's not a particularly good image. And then what we do is we use what's called an evolutionary strategy, where we mutate the parameters and we let this thing run. And the great thing about it is that you can give it a target image. You can see on graphite, you get two types of image. One is this honeycomb, and one of them is this type of trigonal lattice. And sometimes you want to get the tip in a state where you can measure this, or tip in a state where you can measure this. So you can give it a target image and tell it to get there. We just let that one run for 10 hours to make sure that it wasn't going to mutate back into a different state. Anyway, let me just sum that up over time as usual. But I hope that I've put across some of the excitement of scanning probe research, and I hope I've put across some of the frustrations and difficulties with it as well. What we're really going to focus on over the next few years is this idea of tip control, engineering the orbital at the end of the tip, evolutionary optimization of the imaging process, and what I really want to move towards, and has not been achieved to date, is there's been a lot of work in manipulation of atoms on a surface, or even in manipulation of defects in a surface, so two-dimensional work, coupling it all the way back to that madcap stuff at the start, where you were growing large macroscopic structures atom by atom. Can we do a computer-controlled epitaxy, where you grow structures, 3D structures, atom by atom? That's really what we're going to focus on. Sorry for going over time, Rich. Thank you all for your attention.